Okay, so we are going to continue with our functional groups, and you are, of course, going to need your reference tables, right? We're going to be using table R in your reference tables, right? We're going to continue on with our organic functional groups, and this is going to be page number 56 in your notebook. Okay. So a couple of images of just some old timey organic compounds, right? We've got wood alcohol and we have ether. Wood alcohol is what we call methanol, which is not the drinking alcohol. This is a very deadly alcohol. This is the one that can make you go blind and was a big problem during Prohibition. And ether, of course, is an anesthesia. All right, so what do we have? We're going to first talk about alcohols. We're ROH. And so, what again is that R? Right, the R could be any organic hydrocarbon with, and then what makes it an alcohol is if there's an OH group attached to some number of carbons. That's what makes alcohol an alcohol. So, when we have an OH group located on any carbon, and we call that a hydroxyl group or a hydroxy functional group. And so this is an alcohol molecule where, remember, R could be any number of carbons. So how do we name them? Well, we're going to name them by counting the continuous chain of carbons. Like we always do, count. If you don't know what to do and you're stuck, just count some carbons and go from there. So then you're going to count, and we're going to use table P and our prefixes. And so we're going to drop the alkane E, and we're going to replace it with an OL. So basically, anytime you're reading ingredients, anything that ends in OL is an alcohol, OL. So methane would become methanol. And so this is what methanol would look like, right? We basically took an H off of the methane, put the OH. This is our organic functional group. So that's going to be methanol. So then that's what wood alcohol is, and that's the one that's going to cause blindness. Can't drink that one. So then we have ethyl alcohol, or ethanol. So two carbons with an OH is like ethane. We say ethane, drop the E, and add OL. So this is ethanol. So this is the component of many household products, right? Vanilla extract, hairspray, some mouthwashes, but not all mouthwashes. And this is called grain alcohol. And so this is the kind of alcohol that is drinkable, which can be consumed by humans. It's still considered, toxic to the body, especially the liver. And it comes in different concentrations, right? Remember when we did concentration in our solutions unit? Right? So alcohol is a solution of alcohol in water. And if you have 20 proof, it's 10%. So whatever the proof is, you divide that by 2, and you've got yourself the percentage, right? So if you have 40 proof, right, you've got 20% of alcohol. Okay, so 90% of that is going to be water. So this is ethanol. So what are some properties of alcohols? So the solubility of an alcohol decreases as the length of the carbon chain increases. Solubility in water, or because remember, the length of the carbon chain increases, they're less soluble in water because it's going to become a more symmetrical, longer chain. So then methanol and ethanol and isopropyl alcohol, right, those are all soluble in water, low carbons. So now we have butanol. And so this is my little bendy structure, very nicely typed written. But now what does this 2 mean? Well, when I've had numbers in front of things in other parts of this unit, it usually means the location of something. Well, in this case, it is the location of the OH, which is the alcohol functional group. So in this case, the location is on carbon number 2. So I can either go 1, 2, 3, or is it going to be 1, 2? So I need to come up with the shortest number. It's closer to this side of the molecule, so I'm going to count from that side. So that's 2-butanol. So now let's give that condensed structural formula. I have a CH3, and now I have a CH2, a CH, and now remember, look, the OH goes in parentheses like the branch did, and then the CH3. So name draw the condensed formula for an isomer of 2-butanol. So remember, an isomer has the same number of every single element, right? The same molecular formula, different structure. So I think what I'm going to do in this case is I think I'm just going to move the location of that OH, and I'm going to go from carbon number 1, from carbon number 2, I'm going to put it on carbon number 1. So but means 4 carbons. So I'm going to do 1, 2, 3, 4. And I'm going to put it on carbon number 1. So I'm going to do my OH. And then every carbon has 4 bonds around it. And they all have H's. And so this is no longer 2-butanol. Now that this OH is on carbon number 1, this is going to be 1-butanol. Right? So this is the same thing, right? There's my OH, and here's my 4-carbon chain. So 1-butanol. And then the condensed structural formula. All right, so now we have what's called a monohydroxy, primary, secondary, tertiary. And this is some stuff that we're going to end up just kind of really briefly going through that you just don't really need to know about. So we're really at the Regents level focusing on the primary alcohols. Okay, so we have one OH, and it's going to be attached to like methanol and ethanol. Okay, so we're just going to skip over that. I'm going to skip over the secondary and the tertiary alcohols. If you want to look at it, go ahead and look at it. But I'm just going to, for the sake of time, I'm just going to just go past that. Okay, so now alcohols can have more than one OH group. So we can have a dihydroxy alcohol, which means dihydroxy means 2 OHs and the alkane. So here we have 1,2-ethane diol. So here's our carbon chain, ethane, drop, and now we have 2-OL, diol. So this is ethylene glycol. So this is antifreeze. And if you're Stacey Castor, if you followed that case, this is what she referred to as antifree. And again, this is a very, very toxic poison. Antifreeze. Okay, and then now we have propylene glycol, another type of antifreeze. Do you need to be able to know those? No, I just like throwing in some stuff about antifreeze. Okay, so here I have this whole big reading thing, and this is a question. This is a short answer question from a Regents exam. What I like to do is I always look at the question first, then I look at the reading, then the question again, then go back to the reading. So in the space of my answer booklet, I need to draw a structural isomer for a molecule of methane thiol. Okay, so methane thiol, and I need to draw an isomer. So then that means I have methane, right? So I have, right, carbons with 4. And then I have a methane thiol is CH3SH. So CH3, and then I have SH. So, structural formula, not isomer. I don't know why I said isomer. Just a structural formula for a molecule of methane thiol. Okay, that's the structural formula, right? Here's methane thiol, CH3. So I did CH3SH. That's it. All I had to do. Okay, so notice how I have this like solid wedge and the dashed wedge. Those are just some shorthand ways of chemists to indicate how something exists in its 3D space. That solid wedge, right, this solid wedge right here, means that is sticking out of the screen, kind of coming out at the screen at you. And then this means it's going behind the screen, like, so we're looking at, X, Y, and Z axes, basically. All right, so that's alcohols. Basically, for the alcohols, you count the carbons, drop the E, add the ending OL, sorry, and make sure you say what carbon number that OH group is on. All right, so ethers. A patient does not experience pain during surgery when given a general anesthetic. The earliest anesthetics used during the Civil War. So we had anesthetics, like as early as the Civil War. Sorry for all those people who had to endure medical procedures prior to anesthesia. But all anesthesia belongs to a class of chemical compounds called ethers, right? Those were the first anesthesias. So what is an ether? You either get it or you don't. Haha, that's my little chemistry humor. All right, so we have ROR prime, right? Remember that little means prime. So that means I have a carbon chain, an oxygen in the middle, and a carbon chain. Right, so single bonded oxygen located between two carbon chains. So a single oxygen in between two carbon chains. And I usually do this around Easter time, the ether bunny. You either get it or you don't. Please tell me somebody laughed at that. Okay, so how do we name these ethers? So we're going to name the alkyl groups, right? That's just the carbon group, right? We're going to count the carbon chain attached to the oxygen, and then we'll put them in alphabetical order, and we're going to stick the word ether at the end. All right, so here I have an ether. This is a 3D molecule of what an ether looks like. So I have a CH3, and now I have an O, and I have a CH3. So then when I name this, I have a 1 carbon branch and a 1 carbon branch. So this is methyl. Oh, I better erase that. I'll just leave it. This is methyl. So this could be methyl ether or dimethyl ether. And again, these are located on table R of your reference tables. And also what you're doing is you're basically using table R and mimicking what you see in a question to how table R names and draws structures. So this is dimethyl ether. Now let's take a look at this next one. So here's my identifying factor. I look on table R, I identify this as an ether. And because there's only 1 oxygen. There's only a few of them that only have 1 oxygen. And I've got an oxygen stuck in the middle. There's no oxygen double bond. It's a single bond oxygen in the middle that makes this an ether. So then now I'm going to name this as a branch with a YL. Then I'm going to name this with a branch as a YL. So I have a 1 carbon branch. So this is a methyl. And I have a 2 carbon branch. So this is an ethyl. So now alphabetical order. Which one comes first? F or meth? F, right? So this is ethyl, methyl, and now I stick the word ether. Ethyl, methyl, ether. Alphabetical order. Tongue twisters. I love organic compound naming. Okay, so here's my condensed structural formula, right? I've got that CH3, O, CH2, CH2, CH3, O, and then a CH2 and a CH3. So notice I have this oxygen in the middle, and I've got 3 hydrogens over here, and then I've got still 2 hydrogens over there. Right, those are going to be some letter clues. So here I have a 2 carbon branch and a 2 carbon branch in my ether functional group. So I have an ethyl and an ethyl. So I have 2 ethyls, so I can just make that diethyl, and then I'll stick the word in ether, diethyl ether. And here's my condensed structural formula, right? Notice I have lots of hydrogens on either side of that, with those carbons on either side of that oxygen. Okay, so then here I can just condense it even more. All right, so let's draw an alcohol that is an isomer of diethyl ether. So here's diethyl ether. So remember, in isomers, so ethers and alcohols are always going to be isomers of each other, right? Because it just works out well with the way that they're bonding and how many oxygens and how many carbons and how many hydrogens. So I just need to take this OH, this oxygen, and I need just to make that an OH. So I'm just going to take that out, and let's just do this, right? Now I'm just going to squish them all together, and I'll just stick that OH there. How's that? And then here I have those extra hydrogens. Right? Do I still have the same number of each element? Double check. 1, 2, 3, 4 carbons. Yep. 1 oxygen. Yes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. There we go. So there's our molecular formula. And then here is, right? There's more than one place I could do that, right? I could put the OH on the end, or I could have put the OH here, right? There's different places I could have done it. So there was 3 possible isomers. And so now let's name the one that I drew over here is 1, 2, 3, 4, right? So then that's going to be 4 carbons, which is like butane. Drop the E, add OL, and then, right? Drop the E, add OL, and either carbon number 1 is where the OH is, or carbon number 2 is where the OH is. All right, so that's going to wrap up our notes on ethers and alcohols. In our next set of notes, we're going to talk about compounds that have a carbon-oxygen double bond.